Good morning to one and all. Myself Dhaval Chauhan. I am a PhD scholar in Applied Physics Department from the MS University of Baroda. The title of my poster presentation is Electron Scattering for Para-Benzoquinone. Here I acknowledge to FSQT organizing committee to giving me opportunity for presenting my current research work. Here is the basic introduction of scattering theory. In scattering processes, the projectiles with non-kinetic energy are incident upon the target, and after the interaction with the target field, they get scattered and get detected at detector. The projectiles can be electrons, photons, ions, atoms, and targets can be atoms, molecules, clusters, dimers, etc. During this scattering processes, there will be the different changes including like angular deflection, change in kinetic energy and internal energy, chemical changes, gain and loss of electron, etc. Here is the various collision processes. During the elastic collision, two individual particles are scattered without any change in their internal structure. Other all are inelastic channels. We are interested in ionization and excitation channel. The motivation of choosing this molecule because of understanding the unique features and many applications of quinones and its derivative like para-benzoquinone. Application of these in energy harvesting and storage system such as artificial photosynthesis, synthetic platform, rechargeable batteries, pseudo capacitor, pseudo transistor, and many more. Our aim to provide reliable elastic, inelastic ionization and total cross-section data for electron interaction with para-benzoquinone. So we employed these two theoretical methods. One is spherical complex optical potential and another is complex scattering potential ionization contribution. In scope formalism, the Schrödinger equation is solved numerically to obtain complex phase shifts for each partial wave using the Numero method. These phase shifts contains signature of the scattering between the projectile and the target. At low impact energy, only few particle waves are significant, but as the electron energy increases, more and more partial waves are required for convergence. Our spherical complex optical potential is made up of two real potential and imaginary potential. Our optical potential is made up of static potential, exchange potential, polarization potential, and imaginary and absorption potential. These are the model potential. The imaginary part represented the loss of flux into the various inelastic channels. There is no rigorous way to calculate Q ion from Q inelastic, so we have initiated a new semi-empirical complex scattering potential ionization contribution. The other interesting features of this method is it gives total electronic excitation cross-section as a byproduct because the Q inelastic is equal to Q excitation plus Q ion. The CSP-ic approximation originates from the inequality Q inelastic greater than equal to Q ion. When the energy is increasing, then excitation decreases. So Q ion is dominant, so that we are using the semi-empirical ratio. Ratio R is denoted by the Q ion upon Q inelastic. In this equation, C1, C2 and U are the dimensionless parameter. Here is the reference of my current accepted paper. These three conditions which have to satisfy the ratio R is 0 at below ionization threshold, R approaches 1 asymptotically for EI is sufficiently larger than EP. At EI is equal to EP, the contribution for ionization to total inelastic cross-section is about 70 to 80% at the peak of inelastic cross-sections. The theoretical approach of scope along with the present CSP-ic method is employed to determine the various electron impact total cross-section. Here we report theoretical results of electron-driven processes for the para-benzoquinone molecule over a wide energy range from ionization threshold to 5000 electron volt. In figure 1, present Q inelastic, Q ion, Q excitation is computed by scope and CSP-ic method. In figure 2, present Q ion compare with available experimental and theoretical data with Jones et al. And Lozano et al. It gives good agreement with BEB method given by Jones et al. And independent atomic models screening correction additivity rule is given by Lozano et al. In figure 3, the present elastic cross-section is overestimated than Jones et al. And matching with Lozano et al. In figure 4, present total cross-section curve is lower than both available data. Our quantum mechanical theory, it can allow all important cross-section. CSP-ic is semi-empirical theory. It produces reasonable good results. The results are comparable with most experimental study within uncertainty provided by them. Thank you.